Okay, so let us start with the next chapter, that's on counting. Okay, this is a very easy chapter and short chapter. Counting. Okay, so we are in the third chapter right now. You can see now. Okay, so the thing is, we are going to learn different methods to count some quantity as such. Okay, so first we'll study is the counting principles, or yeah, called as the basic counting principles. Okay, so the first one is the first rule is the product rule. Suppose that okay, so what is the rule I'm stating? Suppose that a procedure suppose that a procedure can be broken down can be broken down into a sequence of can be broken down into a sequence of two okay, broken down into a sequence of two tasks, then okay, so if the first task the first task can be performed in n1 ways, okay, and the second task can be performed in n2 ways, okay, if the first thing can be done in n1 ways and second thing can be done in n2 ways, okay, then procedure can be carried out in can be done in n1 into n2 ways. Okay, so basically what we are saying here is that we have n1 options to do the first process and n2 options to do the second process, right? So the total number of options we can get is n1 into n2 options. Okay, come this side of the this number है नहीं एक बेंच खाली हाँ टूटला मस्त. Okay, so let us see examples of this. There are many examples which you can do. Okay, So examples. So first thing, okay, so take this example here. Has two drivers, two drivers and four cars. Okay, so how many ways drivers be assigned to cars? Be assigned to the cars. Okay, in how many ways can the drivers be assigned to the cars? So you have two drivers available and four cars are there with you, right? So yeah, so solution. So the first driver has how many cars possible? He can be assigned to four different cars, right? So driver A can be associated to four different cars. What about driver B? The second driver will get how many possible cars to get assigned to? Three, because one is already assigned to the first driver, right? So 4 into 3, that will give you total 12 assignments. Okay, so 12 possibilities are there. Okay. So next example. Next example 2. Chairs have to be numbered in an auditorium. Auditorium. Okay. Using as follows. The first as follows, comma. The first character is going to be an alphabet. First character is an English alphabet. Okay, followed by a number, followed by a number, no, I won't write number, I'll write integer, followed by a positive integer, integer not more than 100. Okay, so in your movie theaters and all, you have to number your chairs, right? So the rows are given English alphabets and the horizontal number of chairs are given some numbers, right? Okay, so now how many possible chairs can be numbered? How many possible chairs can be numbered? Can be numbered in the auditorium. Okay, how many possible chairs can be numbered on an auditorium, in the auditorium? Okay, so how many such chairs we can do for each alphabet, right? See, the numbers are supposed to be written like this: A1, A2, A3, and so on. It will go on up till A100, right? And this one you'll start with B1, B2, up till B100, right? And this will go on up till Z. Okay, so how many such possibilities we'll get up? We'll get over here. How many such possibilities are there? This will go to Z1, Z2. So there are, in each row there are 100 possibilities, right? Right. So 100 you'll get multiplied by the number of alphabets over here. So 26 into 100. Clear? Now in reality an auditorium does not have chairs like this, huh? Because in some rows they have to put less because of the width of the auditorium and so on. So on, so on. Okay. This is just one understanding example. Next, let us go ahead. Let us go ahead to the next one, third one. Now see, your number plates are something like this, right? GA08. Currently this is this thing going on. Okay. So this is how your number plates are given, right? So now ignoring the first few characters because these are assigned by the RTO. Okay, so ignore this 4 characters. Again it's been the same thing. Okay, but ignore the first few 4 characters. Now let us see the other characters and see how many possibilities are there, right? So this is just like the previous example. How many possibilities are there over here? If you start from 1 and go up till 999, right? This numbers can go from 1 up till 9999, right? Okay, so each alphabet over this, each number can have 9999 possibilities, right? Then what about the next 2 alphabets here? There are 2 alphabetical characters involved, right? So each alphabet has 26, right? So 26 into 26. So this many unique number plates you can get. Okay, clear? But this count is not real actually, because they don't give so many number plates. So many alphabets are not there. See, the thing is, first of all this 9,999 number plates are not given in direct this thing. Some of them are reserved for VIP, like all the numbers between 1, 2, 3 up till 9, I think so, is reserved for VIP use, single digit numbers. Then there are special numbers like 111, then 1, 2, 3, 4, 2, 2, 2. Right, these are sold as lucky numbers. Then there is the many other numbers are there like this in between. Okay, yeah, even 786 is there because many Muslim people buy this number. Right, then you have 999, then 777, then not 7 is counted here on top. Okay, so these numbers are not allotted to people directly. Okay, so this you have to buy on special this thing, so that is not counted here. So this number is not actually 999. In reality, it is a much lower number, right? Also, other than that, not all alphabets are used for numbering. Like for example, the alphabets I is not used because it looks similar to 1, right? So they don't use you. They don't issue this number plates. Also, they don't issue number plates on the alphabet O, right? Because it looks like 0, right? Which are the alphabet they don't give? Yeah, in Goa they don't give this alphabet because this alphabet is reserved only for Kadamba buses. Okay, as of now I don't know, because if they give numbers like AX and all, but X, single digit X was not given to anyone. Yeah, also G is not given. G is reserved for government vehicles, right? Any other special alphabet is there? So like this, if you delete this 3 alphabets, 4 alphabets, sorry, you'll get only 22 working alphabets in reality. So 22 into 22 will give you a much lower number, right? Plus this, I don't know how many actually number plates are kept as VIP number plates. That number I don't have. So, but anyways, it will be less than 999. That much I know. Okay. Yeah. So this is how you can count it actually. Okay. So moving on further to some other example. So okay, some other example. Example number 4. Okay, example number 4. There are 32 computers in a data center, right? Each computer has 24 ports. 24 ports are not parts. So how many ports are there in the okay? How many will be there? 32 computers, each with 24 ports. So total will be how much? 24 into 32, right? 34 into 22, 32 into 24, 24 into 32 you can do. Yes. So next is example number 6. How many defined on a set of n elements to a set of n elements. Okay. So here you have a set of A, the set B. So you have an F which goes from here to. Okay. So if you have a function f which goes from A to B, how many such functions can you have if this has n elements? Okay, so how many such functions can you form? So just think for a moment. So what did I say here? I said that if you can take any arbitrary x, take any arbitrary element in the domain. By definition of a function, it can be assigned to n different choices in B. Okay, n different possible elements in B. So now each element has n different choices in B, right? So what will be the total number of choices over here or possibilities? Okay, yeah. Yeah. So thus for each element, each element we have n possible images, right? Okay, so the first element can be associated to n people, second element also can be associated to n people. Maybe it's a constant function where all people go to the same number in the codomain, right? That can also happen. So n choice for the third element also, right? Dot, 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 dot. Right, n, right? How many times is this going to be? M times. So this is going to give me the answer as n raised to m choices. Okay. Hmm? Each element we have n choices. I just cancelled that out. Okay. So there are functions between a and b. Okay. And different functions between a and b. Please write it. Okay. So the next example here is how many 1 1 functions functions are possible from set A to set B, set A to set B if set A has m elements, set B has to n elements. Okay, same like last time, but only thing I have put the condition here that I want 1 1 functions only. So this one how I will deal with. Okay, so let us work this out. So just like last time, this was supposed to be n, not en. There's n, no? Yeah. So solution just like last time. There is a special case to be dealt with here. If m is greater than n, so that means the domain has more elements than the codomain. In this case, what will happen if there are more elements in the domain than the codomain? To imply that at least one element is getting repeated over here, right? At least one element is getting mapped to the same element in the codomain. Okay. So if m is greater than n, no there are no 1 1. Okay, there are no 1 1 functions because the codomain has less elements than the domain, right? So you cannot have a 1 1 correspondence over there. So some elements have to have a repeated image. Okay. So assume that n is greater equal to m. Okay, assume that m is greater equal to n is greater equal to m. So the first element over here, yeah, so the first element in the set has n possibilities. Second element over there will have n minus 1 because one element is already occupied and I cannot repeat that person. Right? Otherwise it will not be one function. So then n minus 2, n minus 3, and so on. Right? This will go up till n minus m. Okay? This will stop at n minus m, by the way. It will not go up till 1 factorial, 2 factorial. Hmm? Wait. If it is equal to, what will happen? Sorry. It has to be plus 1. See, we started with n minus 0 no, yeah, basically. So n elements have to be counted. So it's going to become okay. Yeah, still the total number of terms which are multiplied are m, count and see. Because the first term which I multiplied was n, it does not have any quantity. Second term was n minus 1, third term was n minus 2. So the m term will be n minus m plus 1. Okay. So this is the number of counts of functions over here. So same way as I shown you about the license plates or the number plates for cars, you can have the same thing for telephone numbers also. Okay, you can do the same things for telephone numbers also. So how many telephone numbers can you get actually? Only the last 5 digits are publicly available for choice. The first 5 digits of your mobile number are kind of fixed. First 4 digits are fixed. Okay. In the olden days, actually, that first 2 digits will tell you the company which your SIM card is with, and then the next 2 digits will be about your circle code or some region code or something. Okay. So basically, the first 4 digits will be preoccupied, and the remaining 6 were available for choice as such. Okay, but now it's not the case because you can port your number from here to there to here, and so on. Right. So, but in like some 10-15 years ago, the numbers were kind of fixed to only the last 6 digits could be chosen. Okay, so there were some people who could actually go to the this thing company and get numbers whatever they wanted. Okay, like there are some people with very specific numbers like 11111 in the last 6 digits. Okay, so that is done. So clear to everyone about the product rule. I'll go to the next rule then. The next rule, that is the sum rule. Okay, this is called as the sum rule. Sum rule. Definition. Done. Can be done. Can be done in either N1 ways. Okay. N1 ways. This looks like Y. Just ignore my handwriting. It's coming bad because I'm sitting like this. Can be done in N1 ways or N2 ways. Then N2 ways in either one of N1 ways or one of N2 ways where neither of nine N1 or N2 ways are common, then the task can be done in can be done in N1. Okay, so if you have two distinct ways where there is nothing common between them, okay, two or more different methods of doing this thing, then the number of ways in which the problem can be solved is N1 plus N2. Okay. Okay, so let us see examples on this. Okay, so moving on. Let's say examples on this. There are 30 students in part 1. Okay, 8 in part 2. Part 2. Part 3. Okay, one student has to be selected as a university as a university representative. Representative. Okay, has to be selected as a university representative. How many choices are there? Representative. How many choices are there? Okay, how many choices are there? What are the possible choices? You can select one of the students from FY. Okay, you can select one of the students from part 1, or you can select one of the students from part 2, right? Or you can select one of the students from part 3. Okay, so according to this rule, are there any students common between all three classes? No, right? So each class is distinct and there is nothing common between them, right? So the total possibilities will be 30 plus 8 plus 7, right? So that is equal to 45. So there are total 45 students available from which one has to be selected. So there are 45 choices. Okay. Okay. So different on this side. There was place to keep my legs there. Now I don't have place to keep my legs. Uh, you legs cutting. Okay, never mind. Anyways, we'll continue. Okay, so moving on. Next example. Can we think of one more example here? There's no example given more on this case. Let me see in the exercise section. Just hold on. Okay, so let's go to the next rule. Okay, the next rule is called as the subtraction rule. Oh, sorry, this is the third one, right? 1, 2, 3. Okay, this is the subtraction rule. The subtraction rule. My handwriting is coming bad now because I don't have this proper angle to sit and write here. I will. Yeah. If a task can be done in either n1 base or n2 base okay, and say yeah, n2 ways. Just write that some ways might be common. Some ways might be common. Some ways might be common to both the this thing. Some ways might be to both. Okay, some ways might be common to both. So then number of ways the number of ways in which the task can be performed is can be done is done is n1 plus n2 minus common ways minus the number of common ways. Common to common to uh, just hold on. Minus number of ways common to number of is common to N1 and N2. Okay. Okay, so let us see examples on this. Okay. A company receive job application job applications, okay, out of which out of which 50 are computer graduates, computer graduate, computer graduate, okay, 60 are MBA grads, 70 are not 70, sorry, 30 are both MBA and computer. Okay, 30 of them are computer and MBA grades. How many applicants are there? How many applicants are there? So think about this for a moment. How many applicants you can have? Okay. So how many possibilities are there? 50 of them I know surely have a computer science degree. 60 of them have a MBA degree, right? And 30 of them are having both. So what you should be doing? What should be done? add and then you have to separate the common. This is one. Close it down. Okay. So you have to add up all the things and separate the common people. Okay. Why are we doing that subtraction, by the way? Because see, when we are adding them up, see when we are adding them up here, 50 plus 60, right? There are some people who are counted here as see, some of these people who have counted here, right? They have this degree also. They have an MBA degree also. So that person is getting counted in this set, and it's getting counted in this set also, right? The people who have both degrees, right? Yeah. So that because of that reason, I have to subtract them once. Okay, because their numbers, they are counted in this set also and they are counted in this set also. So I have to subtract them out. Okay, this will leave you with 50 plus 60, 80 applicants. Okay. So next we'll go to the last method. It's the division rule. Uh, the division rule. Fourth rule is the okay. If a task can be done using a procedure a procedure that can be carried out in n ways. The task can be done using a procedure that can be carried out in n ways, and for each way carried out in n ways, and for each way w, for each way w, each way w exactly, for each way w exactly d of the n ways, exactly d of the dm, and writing will become a bit bad here, d n ways correspond to correspond to correspond to W. Okay, so if a task can be done using a procedure that can be carried out in n ways, and for each n way, each of the way, d of the ways are corresponding to the W, right? Then there are n by d ways of for doing the task. Okay, there are n by d ways of doing the task. Example, there are n by d ways of doing the task. So examples we'll see. This is an automatic is designed count the number of cows cows on a farm. Okay, an automatic system is designed to count the number of cows on the farm by counting the number of legs of cows, counting the number of legs of cows. Okay, if it has counted is counted 572 legs, how many cows are there on the farm, there on the farm. On the farm. Okay, So this is one trick which is used over here. So what does this farmer designed is, instead of counting the number of cows which are manually present over there, on the this thing, farm, what you do is you put sensors over there and you count the legs of the cows. That's a much easier task to do, to count the legs. Okay. Uh, yeah, how is it done is, the cows are allowed to go outside the shed, and when they come back they're entering from a door, right? The door has the sensors near the bottom over there which counts the number of legs which are passing by. Okay, so it has counted that 572 legs have come in or out, right? So how many cows will be there? So you'll get 572 divided by 4, right? Cows. Okay, 572 divided by 4 cows are there. Okay, how much will that be, by the way? This number is 143. 143 cows are there on the farm. This is not only done for cows, this is also done for trains. That I know, it's done for trains like this. If you have noticed, there are some sensors which are kept near railway stations actually, and the signals they are kept. Okay, so the sensors, there are some light coming out of it. So if you are traveling by train, you might have noticed this thing. There is a small light device which is kept next to the tracks. Okay, so that thing counts the number of wheels which are passing by. Okay, so now each coach of the train has a fixed number of wheels over there. Right, so it has a fixed number of wheels. So that is pre-programmed into that sensor. So that sensor counts how many wheels are passing by. Okay, so then as the full train passes by, it counts how many wheels it has counted, and it divides by the number of wheels each coach can have. I think so. Each coach has 8 wheels, on one side. Sorry, 8 wheels in total. So in one side there are 4. Okay, so it will be counting. The sensor will be counting only on one side. So yeah, so it will count how many wheels it has counted, and then it will divide by 4 wheels. Okay, so that will give it the number of coaches that have passed by. So after that number of coaches, it is knows that if a passenger train has only 21 coaches or something, then you can count that after 21 into 4. So how many wheels? Yeah, after 84 wheels have been counted, it can realize that the train has passed by. So it can give accordingly a new signal that the train has passed by. So green signal can be given. Okay, for the next train to pass by or get ready. Okay, so these are some places which this is used. Okay, so that's all in this chapter. It was a very short chapter. Okay, I'll see if I can cover up some new examples in the next class. Okay, otherwise this might be the end of it, but I'll still try to cover up some exercises or something in the next class. Okay, with that we are done. So with that we're done, and then we'll have a 30 marks, what do you call that, ISA for you. Okay, so we'll stop with this today.